All right, let's take a trip. And I mean a real trip. We're going to the very edge of reality, to a place where the force of gravity is so intense, so powerful, that it doesn't just crush things, it actually twists and slows down time itself. So let me ask you this. What if just falling could turn you into a time traveler? Yeah, I know, it sounds like something straight out of science fiction, right? But believe it or not, this is real physics. It's baked into the fundamental laws of our universe. And the key to understanding how it works, well, it's hidden in a force we experience every single second of our life. To really get this, we kind of have to unlearn everything we were taught in school about the most familiar force there is, gravity. Turns out, it's holding out on a pretty big secret. You know, for centuries, we've pictured gravity as this invisible force, this cosmic rope that pulls things together. Isaac Newton's ideas worked perfectly for figuring out orbits and sending rockets to the moon. But then along came Albert Einstein, and he showed us all that the truth was much, much stranger. See, Einstein had this incredible insight. He realized that space and time aren't two separate things. No, they are fundamentally linked. They're woven together into the single four-dimensional fabric of the universe that he called space-time. Everything that has ever happened or will ever happen exists on this cosmic tapestry. Now, to get our heads around this, let's use a really helpful analogy. Just picture the fabric of space-time as a gigantic, perfectly flat, stretchy trampoline that goes on forever in every direction. Okay, so what happens if you take a heavy object, like a bowling ball, and place it right in the middle of that trampoline? Well, it sinks down, right? It creates a curve, a big dip in the fabric. Now, if you roll a little marble nearby, what does it do? It doesn't get pulled toward the bowling ball. No, it just follows the curve in the trampoline that the ball created. That curve, that geometry, that's what we feel as gravity. And the physicist John Archibald Wheeler summed it up just perfectly with this quote. It's this beautiful two-way dance. The heavy stuff in the universe tells the fabric of space-time how to bend. And in turn, that bent fabric tells everything else how to move. So we've got this amazing idea of heavy things making dents in the universe. Now let's see what happens when we take that idea and turn the dial all the way up to 11. I mean, let's take it to its absolute mind-bending extreme. Let's go back to our trampoline for a second. Instead of a bowling ball, what would happen if you put something with just an unimaginable amount of weight and density right in the middle? You wouldn't just get a dip anymore. You would literally tear a hole clean through the fabric. That's a black hole. It's what happens when you crush so much stuff into such a tiny, tiny space that the gravity well it creates isn't just deep. It's a bottomless pit in space-time itself. And every bottomless pit has an edge. For a black hole, we call that the event horizon. Now, this isn't a solid surface you could stand on. It's a threshold. It's the point of no return. The second you cross it, the curve of space-time is so steep that every single path, every possible direction, points inward. There is literally no way out. Okay, so we've set the stage. Massive objects curve space. But here's the real payoff. Remember what space-time is made of? It's not just space, it's space-time and time. And this is the absolute key to everything. Because time is woven into that cosmic fabric. When extreme gravity stretches and warps space, it does the exact same thing to time. It stretches time out. Physicists call this awesome effect gravitational time dilation. So to really see what this means in human terms, let's run a little thought experiment. Let's imagine we have two identical twins. One of them stays here, safe on Earth, but the other one hops in a spaceship and goes on a trip to orbit really, really close to a giant black hole, just outside that point of no return. The difference in their experience of time would be staggering. I mean, it's just wild. For every 10 years that pass for the twin back home on Earth, our astronaut twin deep down in that gravity well might only experience one single hour. Her clock is literally ticking slower. She is aging slower. But, and this is the key part, for the astronaut, everything feels completely normal. Her heart beats normally. A movie still takes 2 hours to watch. From her perspective, time is just fine. So if everything on her ship feels normal, where's the weirdness? Well, it's what she sees when she looks out the window. From her vantage point, she would see the entire rest of the universe playing out in fast forward. She'd see stars zipping across the sky, entire civilizations rising and falling. It would be like watching a cosmic movie with the playback speed cranked way up. So what does this all add up to? If our astronaut hangs out there for what feels like just an hour, and then flies back to Earth, what is she gonna find when she gets home? Let's just quickly put the big pieces together. 1. Gravity isn't a force pulling us down. It's just the shape, the curve of space-time. 2. Black holes create the most extreme, the most intense curves in the entire universe. And 3. The absolute kicker. The deeper the curve, the stronger the gravity, the slower time itself actually flows. So our astronaut lands back on Earth. For her, it's been an hour, maybe she's ready for lunch, but for everyone she left behind, 10 years have passed. She didn't go back in time. No, by slowing her own clock way down, she effectively took a giant leap into Earth's future. And this leaves us with one final, just haunting thought. As you get closer and closer to that event horizon, the time dilation gets more and more extreme until, right at the edge, time, from an outsider's perspective, slows to a complete stop. You'd be frozen for eternity. So what does it even mean for time to stop? Well, that's a question that pushes the absolute limits of physics and our own understanding of reality.